Ladies and gentlemen, hello and welcome once again, coming to you not quite live from One Take Studios, where we've got exponential and logarithmic equations to solve today. Always fun, and I actually do mean that, although some people have insinuated that maybe I'm a little bit unbalanced, so take it for what it's worth. Alright, there are essentially two strategies when approaching exponential and logarithmic equations. Textbooks may or may not have names for them. Naturally, I named them so that I can refer to them. The first one in my brain is called Equating Sides. And it's a strategy that's relatively logical, but not often used. Oftentimes you're thinking about, can I get x by itself? And oftentimes that's something good to think about. But if I have an equal sign, that means that what is on the left is supposed to equal what is on the right. That means that if I have corresponding parts between the left and the right side, pieces over here that match up with pieces over here, then the pieces parts from one side to the other must also be equal, and we can use that to our advantage. All right, I'll show you some examples here in a second. The second one I call changing forms. I know that textbooks don't teach it this way. Quite frankly, my method achieves the exact same thing in one step less, so haha. All right, changing forms is simply this, saying, all right, if I've got something in exponential, and I need to get at something in that power, let's change the form. Let's rearrange it. Let's get that power down something that I can solve for. Or, conversely, if I have this and I'm trying to get at some of the pieces here, I can actually change it and put it into exponential form to finish solving. So if it's in one form, try the other. If it's in the other form, try the first. All right. I have 4 examples for you today, 2 from each type, 2 from exponential, 2 from logarithmic, and fascinating as always. So the first 2 examples are going to be exponential examples. Waiting for the camera to focus. Thank you, thank you. All right, so what I have is 9 to the 8 minus x equals 27 to the x minus 3. If I'm looking at this, I'm going, it doesn't really look like this, because my answer piece is a whole other exponential piece, so I'm probably not here, I'm probably here. So if that's true, and I've got an equal sign, that means that the left side truly has to equal the right side. But the way I'm currently looking at it, the 9 and the 27, the base on the left and the base on the right, those aren't the same. But could they be? Could I do something with that to make that happen? 9 can be written with a base of 3, 27 can be written with a base of 3. Hey, let's think about this. 9 is 3 squared, and 27 is 3, that's not a 3, is 3 cubed. Can we use that to our advantage? Yes, we can. All right, so really, we're saying this is 3 squared to the 8 minus x power. In other words, this is a power being raised to a power. If you do not know what your properties of exponents are, you better go dig those out someplace and look at them, because I'm going to reference them as though you actually remember them. Right, okay. So if this is 3 squared, a power being raised to a power, you multiply the exponents, so this becomes 3 to the 2 times 8 minus x power. 3 to the 2 times 8 minus x power. And then same thing over here. This is 3 cubed to the x minus 3. Power being raised to a power, you are going to multiply the exponents. Now let's look at this, all right? The base on the left is 3. The base on the right is 3. So if you talk about corresponding parts being the same, I'm in a good spot right now. So if the base on the left equals the base on the right, then the exponent on the left must equal the exponent on the right. Think about what I just said. The exponent on the left, 2 times 8 minus x, must equal the exponent on the right, 3 times x minus 3. What happened to my base 3's? Did I subtract them? No. Did I divide them? No. What am I doing? I'm ignoring them. They no longer matter. If the base on the left and the base on the right are the same, they're not the important part of the equation anymore. Now I can focus solely on the exponents, which now gives me an equation to solve that I'm kind of comfortable solving. So this is going to be distribute. This will be 16 minus 2x equals, that'll be 3x minus 9. I'm going to add the 2x to both sides. That puts a 5x over here. I'm going to add the 9 to both sides. That's going to put a 25 over here. I'm going to divide both sides by 5, and guess what? X equals 5. Boom. There we go. Ta-da! All right. That's one. So that is one approach. If I can get the base on the left and the base on the right to match, I can ignore the bases and just focus on the fact that the exponents must also be equal and solve. All right, so what does that mean for something like this? Well, if I'm looking at this one, can I get 4 and 5 to be written in the same base? Well, 4 can be base 2, 5 can be nothing useful. I can't rewrite 5 as a base of anything. Alright, so equating sides may be not the best option here, but I do have something that kind of looks like this. So maybe I change forms. Maybe I rewrite this and say, okay, I'd like to get at that power right there. What if I could get it down so that it's not an exponent anymore? What if I rewrote this and called it instead log base? Alright, so what's the base? The base is 4. Answer, remember doing log BAP here, the answer was 5. So log base 4 of 5 equals, the power is here, so x minus 1. Check it out, people. I'm one step away from having x by itself. Yeah, I just have to add 1 to both sides. So that's going to be log base 4 of 5 plus 1 equals x. Please notice I'm not taking the log of the 1, it's just being a plus 1 tagged onto this 5 right here. Could I leave my answer like that? Yeah, actually I could, or I could put that in the calculator. If I do log base 4 of 5, that actually gets me 1.161, in which case I can add 1 and get a total of 2.161, and that would be an approximate value for x. So depending on what you got going on in class, maybe you've got somebody who would rather have you leave it in this form and call it log base 4 of 5 plus 1. That's a reasonable answer, but you can get the decimal equivalent as well, and that'll work. All right, 2 down, 2 to go. Those were exponential equations. What if we have stuff that is logarithmic? Sounds interesting. All right, I made one of these intentionally much more interesting than the other because that sounds exciting. All right, so this time around we got logarithmic equations. Same 2 strategies though. Okay, so here we go. I've got log base 7 of 3 minus 4x equals log base 7 of x over 3. Notice the parentheses, I'm taking the log of the whole chunk here and the whole chunk here. Is this something that looks like this? Not so much, because this has 1 log and this has 2 logs, 1 log on each side. So maybe again equating sides makes more sense. There's a log on the left, log on the right, corresponding parts match. Base 7 on the left, base 7 on the right, corresponding parts match. If all that is true, and the left side really does equal the right side, what that means is that this answer piece, so to speak, again, it doesn't really have a name. That makes me sad. 3 minus 4x must equal this piece on this side, which is x over 3. I can write that better. I'm going to squish it, though. X over 3. So if the left equals the right, and pieces parts of the left equal pieces parts of the right, then the remaining parts, 3 minus 4x, must equal x over 3. There we go. Solve. Get x by itself. I'm going to start by multiplying both sides by 3. If I multiply both sides by 3, this gives me 9 minus 12x equals x. And then, oh, let's see what we do here. Oh, we can add that. That'll be 9 equals, that's a 13x. Oh no, it's not coming out perfectly. So, I can still divide. 9 divided by 13 equals x. There's my answer. Ta-da! That's it, right there. Not terrible. Can they get more terrible? Of course they can. Alright, so here we go. Last example. It's a doozy. Are you still paying attention? This is not the time to tune out, people. Not the time to tune out at all. Okay, so here we go. What the heck is this? Well, okay, so this had a log on the left and a log on the right, and this does not, but this also doesn't look like this guy, because this guy's got 1 log, this guy's got 2 logs. Could I subtract a log to the other side? Maybe, but I still have the 2 sitting there, so how does the 2 fit into the picture? It doesn't, really. So, remember over here, we said, hey, we might need to make use of our properties of exponents? Maybe you should also find your properties of logarithms. Ooh, yes, that's a thing. If I am adding 2 logs with the same base, by the way, I don't see a base number, that means that they must be automatically base 10. So I can add this log to this log through the use of addition? Wait, no, through the use of, we're adding its multiplication. If that makes no sense to you, look up your properties of logarithms, because again, I'm kind of referring to them like they mean something. X times x plus 48. That is how our properties of logarithms work. We can take this from 2 logs to 1 log, keep the base the same, and just multiply the x times the x plus 48. All right, was that useful to us? Well, yeah, actually it was. If you want to do big old giant brackets here, you can, because we are taking the log of that whole thing. But now I've got one log on the left. Oh, look, that kind of looks like this one. So maybe I could rearrange it. That would be nice, because I can't subtract log from both sides. That doesn't work. I can't divide log from both sides. That doesn't work. Log is its own operation. Log can't be undone by any of our traditional operations. But logs and exponents are inverses of each other, so changing forms will undo the log. So if I think I've got this, and I want to write it like this, the base here we said was 10. 10. I'm going to, what am I going to do? Now I can write it here. Okay, so 10, and let's see, we're looking at this. So the power is 2, so that's 10 squared, equals, the answer chunk from here goes here. So x times x plus 48. Now, in theory, you should be fine. Because in theory, you should be looking at this and going, hey, it's quadratic, and I know how to solve a quadratic. Yes, but I know some of you. Guys, everything you've ever learned about solving still works. And you have to remember, you can't just wipe it out of your brain and call it good. You have to be able to solve a quadratic. Can you? Let's find out. 10 squared is 100, so I like that. I'm going to distribute my x. We'll call that x squared plus 48x. And then, solving quadratics, that usually involves getting it equal to 0. So let's call it 0 equals x squared plus 48x minus 100. Oh no, whatever shall I do? I'm going to factor, because this one factors, and to me that's the easiest thing to do. Could you use quadratic formula? Yes, it'll take you twice as long, and you may not end up with the correct answer, because people do silly things when they do the quadratic formula. So, what is this going to be? I'm going to call this x and x, and I know it's got to multiply to make negative 100, add to make 48. Ooh, this is not bad. I can do a 50 and a 2, because 50 times 2 is 100. I need a positive 48, so let's do a plus 50 and a minus 2. So, first makes first, last makes last. Oi gets you your middle term, so this is minus 2x plus 50x. Boom. There we go. How do I finish solving? If this factor times this factor equals 0, then one or both of these factors must equal 0. Therefore, x must equal, if I look at the first factor, if I set that one equal to 0, I get negative 50. And if I set my second factor equal to 0, I get 2. Cool. 2 answers. Great. Awesome. Why hasn't she boxed the answers yet? What's wrong? There must be something wrong. There is something wrong. We did everything right, and this is not the right answer. So what just happened? Are you paying attention? Still? I'm going to take this negative 50, and I'm going to go back to just this first log right here. I'm going to say, what is the log of negative 50? So I'm taking my answer, and I'm just plugging it in just to that first piece, the log of negative 50. Well, let's think about what that means. That means that we are saying 10, because that is a log base 10, to some power that we do not know, to some power would have to equal negative 50. I want you to think very carefully. How many times can you multiply 10 times itself before it equals negative 50? Oh, that's right. You can't. This doesn't work. Therefore, this doesn't work. This is what is called an extraneous solution. Extraneous solution. So, E-X-T-R-A-N-E-O-U-S means it is a solution, but it's an extra one that we don't need that doesn't actually work, and the only real answer to this is 2, because I can put a 2 here. I can do 10 to some power equals 2 because 2 is positive. So, do I have to automatically then get rid of all negative answers? Careful, please be careful. Some of you have to just tell me what to do and I'll do it. I'll get rid of the negatives, it's fine. You're going to have to think. You're going to have to take your negatives and plug them back in to see if they work or not. Sometimes you can keep the negatives. Frequently you can't, but sometimes you can keep the negatives. So if you get a negative answer and you are working with logarithms, all right, note to self, go back. Plug them in, take a look at them, see what you can keep, and see what you can't. All right? Eyes open, brain open. This is going to require practice. All right? So time, patience, go for it. Have fun.